So today we're going to go over binomial expansions with negative and real exponents. I assume everyone's familiar with the original binomial expansion formula, which states that a plus b to the power of n is equal to, from sigma, from k equals 0 to n, a to the power of k times b to the power of n minus k times n choose k. Now, in this formula, n is normally assumed to be a positive integer. But in fact, n can actually be negative and even real, like a decimal number. So what do we do when that happens? So I'm going to go over the derivation of negative exponents first, and then I will show you how you can calculate negative and real exponents from just this formula alone. Now, the idea of negative exponents comes from the geometric series. So, let's start off with a very simple geometric series. 1 plus x squared plus x cubed to infinity. Now, what is the sum of this geometric series? We're going to assume that the absolute value of x here is smaller than 1, but x is basically a dummy variable, so the real value of x does not really matter. If we were to let this be s, then xs would be x plus x squared plus x cubed plus x to the 4, so on and so forth. Then s minus xs would give 1, because all the terms after 1 cancel each other. Then s would equal 1 over 1 minus x. Now, we can rewrite this as 1 minus x to the power of negative 1. So, we know that 1 minus x to the power of negative 1 equals 1 plus x squared plus x cubed, so on and so forth. Now, how can we generalize this to a plus b to the negative 1? Well, let's rewrite a plus b to the negative 1 a little bit. So what will we get? We get a plus b, or 1 over a plus b, which equals 1 over 1 plus b over a times a. So what we did is we factored an a out. So this equals 1 over a times 1 over 1 minus negative b over a. Now, note that this now matches the form of the original that we had up here. So all we need to do now is let this negative b over a be x. So we have 1 over a times 1 plus negative b over a plus negative b over a squared plus negative b over a cubed, so on and so forth. Now note that this is an infinite expansion, so this does go on forever. But this is your general term for negative exponents. Now, what if we, let's say, had a plus b to the power of negative k? Well, all we have to do then is just write this as a plus b to the power of negative 1 to the power of k. And then we can just substitute what we had up here. So that's 1 over a times 1 plus negative b over a plus negative b over a squared plus negative b over a cubed, so on and so forth, to the power of k. Now, this is especially useful in something called a generating function. But that is a topic for another day. Now, we can actually also come to this conclusion just by using the formula that all of us are familiar with. So, and this is what we're going to do with decimal exponents. So now let's say we are given an n that is a real number. So let's just take a closer look at this formula here. We have a plus b to the power of n. This is equal to n choose 0, a to the 0, b to the n, plus n choose 1, a to the 1 times b to the n minus 1. And essentially, this number keeps increasing by 1, this number keeps decreasing by 1, and this number keeps increasing 1 until you get to n, right? Now, this is assuming that n is an integer, in which k will perfectly match up with that integer, and we know when to stop. But when n is a real number, we don't have that luxury of k matching up, which means we're just going to have to keep going with our expansion. So what this means is that when k is a real number, this expansion just continues going. We don't have a term that we can really stop at. Now, the computation of this usually isn't too terrible, even though this is an infinite sum. Generally, one of these terms, a and b, would be quite small, and as a to the power of k approaches infinity, usually that would go to 0, right? And same thing, once k here, and choose k, reaches a certain point, when k is greater than n choose k also becomes 0, because you can't choose greater numbers, right? Obviously. Now, but what about all these terms in between? How do we compute them? Well, we know how to compute a to the power of k, real number to the power of a real number, b to the power of n minus k, real number to the power of a real number. But what about n choose k? Well, n is not really an integer here. So what does it really mean to choose k things from a decimal amount of things? Well, if we recall the formula for n choose k, we have n factorial over k factorial times n minus k factorial. And I'm going to write some of these terms out all the way to infinity this time. So same with the factorial, we don't have the luxury of stopping at 0. We're just going to have to keep going until negative infinity. Same thing for the bottom. So k factorial we can keep. But n minus k factorial, same thing. That's going to be a decimal. That's never going to stop at 0. But what we can do here is we can notice that everything past a certain point in the numerator will cancel out with the denominator. In fact, the last term here should be n minus k plus 1, as it doesn't cancel out with anything in the denominator. And what we're left was this. N times n minus 1 times n minus 2, all the way to n minus k plus 1 over k factorial. So that's how you can compute each term in a binomial expansion with real exponents. And we can do the exact same thing if we wanted to use this formula as the way to solve this if our exponent was negative. In the exact same way, we don't have that luxury of being stopping at 0, and k doesn't really stop at n. Instead, we're just going to have to keep going until infinity. Now, let's do an example problem here. So, find the first three terms of I think it's 1 minus x over 4 plus x. Right, so what we can do is we can rewrite this over 4 plus x as 1 minus x to the power of 1 times 4 plus x to the power of negative 1. So 1 minus x we can keep here, and we're going to use our formula that we derived earlier for our negative exponents, right? So that's going to be 1 over 4 times 1 minus 4 over x, I believe. B over a. Nope. So x over 4, my apologies, x over 4 plus x squared over 16. And since we only want the first three terms, this is going to suffice. So this does technically continue on forever, but we don't really care about the terms after that. So what we're left with is 1/4 minus x squared minus 16 plus x squared minus 64. And expanding this gives 1/4 minus x squared minus 16, or not x squared, same here, plus x squared over 64 minus x over 4 plus x squared over 16 minus x cubed over 64. Now that's going to be part of the fourth term, so we don't really care about that. But we can combine our first three terms. We get 1/4 minus should be 5 over 16x plus 5 over 64 x squared. And that is our answer.